So let us visualize one communication system whereby we have a message signal x of t and we are sending it over the air by means of an antenna, and at the other end of the transmission we have y of t. Now this end may represent a linear time invariant system which includes antenna 1, channel, antenna 2. So the received signal, that is y of t, is basically the input signal x of t, but now we would have some sort of time delay over here, so we would have x of t minus the amount of delay that we'll get, that is td, and then this LTI system would have some sort of attenuation, and let us denote that attenuation by a factor k. Now if we take the Fourier transform of this signal, so we have y of f which would be equal to x of t, so we have x of f, and then from here now we have time shifting property. So if there is a time shifting property, so in the frequency domain we have e to the power minus 2 pi f and this amount of delay, that is td, and moreover this constant coefficient from linearity would appear as is. So hence we have x of f and h of f. So h of f is basically the transfer function that is representing this linear time invariant system. So now from here we have h of f, which is simply k e to the power minus 2 pi f td, and from here the magnitude of h of f is simply k, this factor, and the angle, the phase of h of f, so let's call that this is theta h of f, this is simply, there's a j here, so this is simply minus 2 pi f td. So as we can say that if we plot the spectra, that is the magnitude plot and the phase plot, so we have a constant amplitude, that is k, at all frequencies. So this is denoted by this equation, and then from here we know that the phase is basically linearly dependent on frequency as td is constant, so we would have an odd function like that. So that is, this theta h of f is represented by this function, and this is represented by the magnitude, that is k. So therefore a distortionless transmission or a distortionless system is such that you have the same frequency amplified by k. K could be 1, it could be greater than 1, or it could be less than 1, but it is having the fixed value for all frequencies, and then this phase is basically linear with respect to frequency. So these are the conditions that the system must satisfy, but we know that from this we can observe that if the system is behaving and it's giving as a constant value of k across all frequencies, so taking the inverse Fourier transform, so this is going to give us a function which is simply a delta function available at time instant 0, and the strength of this delta function is k, that is, the height is infinity, the width is approaching 0, but if you take the area or the integration of this function, so that is going to give you k. So we cannot generate this kind of function, so we will not have any filter which has an infinite bandwidth and it is having a delta function in time domain. So in short, we would not have this kind of a behavior in practical circuits. But at the same time, usually we are interested in specific band. For example, if we are considering a low pass filter, and in this low pass filter we have the transfer function or the response where certain frequencies of bandwidth say b. So over this range, in this range we say that all frequencies has a constant amplification of k, and we also want to ensure that over this range from minus b to b the phase is also linear. Beyond this range it may be nonlinear, but we want to ensure that over this range the system or the filter behaves as a distortion-less system. So, but the question is this system practical? To address that, again, we will take the inverse Fourier transform of this function. So, in time domain, this is a rect function. So, if in frequency domain we have a rect function, so in time domain we have a sinc function. So, say that sinc function is available at time unit 1, that is it's having a maximum amplitude at 1 and its zero crossing is at 0. So if this is the transfer function of a low pass filter, so this after the inverse Fourier transform would be h low pass filter of t, that is the impulse response of that filter. But you can observe that this h of t is available for time period when it is less than 0. So if it is available for time unit of less than 0, so this means that this belongs to non-causal class. So it is not practical. So this means that originally over here, based on this definition, we said that this system cannot be implemented and it is not a practical system. So we relaxed our assumption of minus infinity to infinity and rather we restricted ourselves from minus b to b, right? And we said that we are going to have a constant gain of k over this range, and the phase would also be linear with respect to frequency. But still this is non-causal and hence it's not practical. So we can make it practical by multiplying with the unit step function. So if we multiply the impulse response of a low pass filter, ideal low pass filter with the unit step function, so this would mean that this region would become 0 and this would be as is. So we have now this response which is like that. So this would simply be h hat low pass filter of t, that is the impulse response, estimated impulse response when we are multiplying the actual impulse response with the unit step function. Multiplication of unit step function has changed the behavior of a system in time domain. So this frequency spectrum or the frequency plot would also change, and we would lose this sharp cutoff and we would have something like this at the edges, and there will be some transitions over here. So in this way the filter or the system is becoming more and more practical. Now let us look into one such practical filter that is implemented in real life, and let us take an example of the first order filter. So for the low pass filter we have input Vi of t and then we have a resistor a capacitor, and at the output we have V output of T. So say the resistor is of 1 kilo ohm and the capacitor is of 1 nanofarad. So this is our V output of T. So we have the output, that is V output of T. So this is equivalent to V input of T convolve with this system, and that is H low pass filter of T. So now if we take the Fourier transform of this, we have V output of F, this is V input of F, and this is simply from the voltage divided rule. So we have the impedance, the characteristic impedance of capacitor divided by ZC plus ZR. This is our filter response, that is low pass filter of F, and it is equivalent to this function, which is 1 over j 2 pi fc divided by 1 over j 2 pi fc plus r. So this is actually equivalent to 1 over 1 plus j 2 pi f rc. So for this system, the magnitude response, that is H low pass filter of F, the magnitude of it is simply 1 over under root a square plus b square. So we have 1 over 1 plus 2 pi f rc square under root, and the phase is simply tan inverse of this function, that is minus 2 pi f rc. Now for the low pass filter, now the magnitude and the phase equations are rewritten over here, and we have set the frequency range, that is minus 1 e raised to power 7 to 1 e raised to power 7. So the resistor is 1 kilo ohm, capacitor is 1 nanofarad, and under these conditions then we have plotted the magnitude and the phase plot. So this is the magnitude plot, this is our phase plot, and this is the magnitude square plot. So you can observe that the bandwidth that is from the magnitude response, the bandwidth is from 0, and this gain is decaying, and it would reach 0 when the frequency would reach infinity. So this is a decaying function, sort of an exponential decaying function. So the absolute bandwidth is from 0 to infinity, that is infinity. But since we are considering the low pass filter, so you can observe that there is a constant decay. So there is always a distortion, or in terms of phase, you can observe initially there is certain region where it seems to be a little bit linear at low frequency, and then we have a non-linearity, right? So we are indeed interested in this range, where the phase is linear and the magnitude is as linear as possible. So as mentioned, the bandwidth is from 0 to infinity, but we are interested in a meaningful bandwidth. Say that meaningful bandwidth is half power bandwidth. So hence we may be interested in the half power bandwidth. So from this expression we have, so this is 1 over 1 plus 2 pi f rc whole square, and the maximum power of the low pass filter is over here, that is 1, right, when the frequency is 0. So we have a low pass filter of 0 whole square divided by half power. Half power would mean that wherever we have the maximum, so we divide that by 2. So presently in the low pass filter, the maximum is at DC value at 0 frequency. So we divide this by 2. So hence we have 1 over 1 plus 2 pi f. We already know the value of resistor and capacitor, so these are known. So this is equal to 1 by 2, and from here we can find f naught, this value, and this would be simply roughly 9 kilohertz. So over here at 0 we have the value of 1. So half power means we are interested in 0.5. So zero point 0.5 is roughly about here, and this frequency is nothing but 159 kilohertz. You can observe that it is almost linear from 0 to 159 and minus 159 hertz, and over here we have a decay, right? So it's not having a constant gain, so this is having distortion in this region. So as this is our half power bandwidth, 0 to 159 kilohertz. Now next we are interested in 0.9% of the magnitude over here. So if the magnitude drops from 1 to zero point 0.9 and we set the bandwidth to 10 kilohertz, that is 0 to 10 kilohertz, and we allow the attenuation to drop up to 0.9. So for that, what are the values of resistor and capacitor that are desired? Now we have the bandwidth of 10 kilohertz, that is now the cutoff frequency f naught is simply 10 kilohertz, and at the same time the attenuation can go up to 0.9, that is the attenuation level should be less than or equal to 0.9. So that is now we have 1 plus 2 pi f naught, which is now 10 kilohertz, and RC square. This is now equivalent to, and the maximum power that we have is basically 0. So the square of that, and then we are applying zero point 0.9. So we are applying zero point 0.9 square or simply absolute square. It would not make much difference. So that is in terms of magnitude and not the square of magnitude. We are allowing something like this. This is 1 and this is 0 0.9. This is our f naught. So hence this would simply be, because at 0 this magnitude is 1. So from this expression we can have the composite value of RC, which is 6.67 into 10 power minus 6. Now using this combination, the complete value of resistor and capacitor, and finding this resistor and capacitor based on this complete value, we can achieve this design goal. Now herein we have the circuit for a bandpass filter. So we can find the transfer function, the frequency response of this filter. Now this is basically the example for the bandpass filter just shown. So we again set the frequency range, the value of resistor that is as before, and then we have an electro value which is 1 millihenry, and the quality factor Q resonance frequency f naught, right? So plotting the magnitude and phase of bandpass filter. So we have these plots: the magnitude plot, the phase plot, and the magnitude square plot. So note that the magnitude square plot also defines how much power is available at a given frequency. So if you integrate from 0 to infinity this function, right, and then multiply that by 2 because this is an even function. So if you integrate this and multiply by 2, so you're also covering this portion, right? So you will find the total energy or power of the signal.